right now.
We're on.
Welcome everyone. And thank you, Vint Cerf, very much for accepting our invitation for the Washington Academy of Sciences seminar series. Hi everyone, I'm Ram Sriram, and I'm the president-elect of the Washington Academy of Sciences. Today, Vint Cerf is going to talk about lessons from internet. And many of you probably know Vint. Vint is considered as one of the fathers of the internet. In fact, today we are doing the Zoom meeting because of the work that Vint has done several decades ago. Vint has got many accolades, and if I have to go through the list of all those, it'll probably be the entire 1 hour. So I'm going to summarize a couple of them quickly. He's a recipient of the Turing Award, which is considered as a Nobel Prize in Computer Science. He's also received the National Medal of Freedom, I believe. Vint has got other awards like the Japan Prize, and all of them very, very prestigious. And he has had an impact on the life of many of us. So without much ado, Vint, can you take over?
Well, thank you so much, Ram. I have to tell you, it's ironic that today I got my notice of dues for the Washington Academy. I didn't know whether that was carefully timed to remind me that you turn off my microphone if I didn't pay my dues. I also thought I would practice my stand-up routine, even though I'm sitting down right now. And so I'm sure these are signs of the times. I mean, I'm sure you've all seen these as we've tried to live through this online environment. Then the Supreme Court ran into this problem. And so we have that one. And then, of course, because the virus is with us, you've got this one as well. So those are signs of the times. I'm going to try to share my screen so that we can have a look at a few illustrative slides. So let me see if I can get this to work. There. I'm hoping now that you can see something that says lessons from the internet. Is that correct?
Yes.
Okay, that's great. So these are really accumulated experiences over the course of nearly 50 years. But I wanted to start out by showing you something that happened over 100 years ago. This guy, Duell, he was commissioner of the Office of Patents, and in 1899, he says everything that can be invented has been invented. So I think we have news for him 100 years later that there's still plenty of inventions that are being created. Here's another more recent one. Paul Krugman, back in '98, thought that the internet wouldn't be any more important than a fax machine. And what's astonishing is that he asserted that after the World Wide Web had arrived, some 7 years afterwards. And so I am sure that Paul, if he were confronted right this moment, would agree that that was a lowball estimate. And this one, of course, is my favorite one. And I think anyone in science and technology agrees that the closer you look at anything, the more complicated it gets. And that, I would say, is a real, true lesson for me anyway. Let me take you back to 1969. I guess it would be helpful if people would mute if you're not speaking. This is what the small little ARPANET experiment looked like way back in 1969. It was an attempt to determine whether or not packet switching technology would actually work as a way of connecting computers to each other. The other alternative would have been circuit switching, which would have been the conventional wisdom at the time. But circuit switching is slow, and you can imagine computers wanting to I'm still getting a lot of background noise. I'm not sure where it's coming from.
Vint, can I interrupt for 1 second? I think there is a lot of background noise from someone. So please, can you all mute? Otherwise, we have to physically kind of mute you, everyone here. And also, at the end of this talk will be for about 40 minutes. And then if you have any questions, please put it on the chat. So please mute again. And any questions, put it on the chat. Vint, go ahead. Sorry about that.
This is what we would call netiquette in the 21st century. So anyway, our experiment was to take these blue colored dots, which are packet switches. Today we call them routers, but they were a uniform homogeneous network that would take these little bursts of data from each of the computers. And I want to emphasize that these computers were from all different brands. The 940 and the Sigma 7 were from Scientific Data Systems, the 360 from IBM, and the PDP 10 from Digital Equipment Corporation. So we were trying to interconnect computers of different brands with different word sizes and different operating systems through this uniform packet switched network. And it worked. I mean, this was a spectacularly successful experiment. And in commemoration of that experiment, 25 years later, two of my colleagues and I, Steve Crocker and John Postel, posed for this picture in Newsweek magazine. It took us the entire day to set up the shot, draw the pictures in the background, find the zucchinis and the yellow squash and the coffee tins to assemble this picture of the primitive technology of the ARPANET of the time. And those of you who look carefully at this will appreciate this. This is a geek joke, because it's ear to ear and mouth to mouth. There was no mouth to ear in this picture, and it never would have worked. And that was our contribution to geek humor way back in 1994. Well, Bob Kahn and I met in my laboratory at Stanford University in 1973. And he said that ARPA, the Advanced Research Projects Agency, having been satisfied with the ARPANET's success, then said, why don't we try to use computers in command and control, which implied that some of them would be in ships at sea, some would be in aircraft, and some would be in mobile vehicles. But the ARPANET had been built around dedicated telephone circuits connecting those blue packet switches to each other. And you can't use wires to connect the tanks and the airplanes and the mobile vehicles. So Bob had already begun in 1973 to design and build a mobile packet radio system and a packet satellite system over the Atlantic to connect the west coast of Europe to the east coast of the United States using Intelsat 4A. So at this point, around 1976 or so, I left Stanford and joined ARPA to run the internet program at ARPA, the packet radio and packet satellite and packet security programs as a package deal. And so as the program manager, I was eager to demonstrate the TCP/IP protocols that Bob and I pioneered and published about in IEEE in 1974 actually worked in a diverse networking environment. So the picture you're seeing now is what the internet looked like in late November of 1977. We had a mobile radio van running up and down the Bayshore Freeway in the Bay Area, and it was radiating packets through the packet radio network into a gateway that led into the ARPANET. And by that time, the ARPANET was actually extended to Europe with an internal satellite hop to Norway and then a landline down to the University College London. So we caused the packets to go from the radio van all the way across the ARPANET to London, and then it popped out through another gateway and back into the Atlantic satellite system, through that satellite hop back to the east coast of the US, and then through another gateway and back into the ARPANET again, and then down to Los Angeles. Now, the physical distance between the Bay Area and USC Information Sciences Institute is about 400 miles. But the packets traveled 100,000 miles because they went up and down to synchronous altitudes, back and forth through two satellite channels, and of course, across the US and the Atlantic Ocean twice. So the packets went 100,000 miles, but the actual distance of communication was only 400, and it worked. And I remember I was in my office in Washington, DC at the time, jumping up and down saying, it works, it works. And I was thinking, this is what you say when any software works at all. It's a miracle. So I was very happy to be able to argue that the TCP/IP protocols could successfully link very different packet switch nets with different error rates, packet sizes, addressing structures, and latencies, and bandwidths for that matter, and still appear to be uniform to all of the computers that were part of the system. So that was a very important milestone, certainly for me anyway. The American research establishment, noting the success of the internet at ARPA, invested in its own implementation of backbone networks based on TCP/IP. And so the Computer Science Network gets started by NSF in 1982, followed by the NSFNet backbone and a dozen or so intermediate level networks to connect 3,000 universities in the US to the 5 supercomputer centers that NSF was funding jointly with the Department of Energy. The Department of Energy decided to link all of its laboratories together with its own internet backbone, and NASA similarly linked all of its laboratories together with its own NASA Science Internet backbone. So we had 4 government-sponsored backbone networks, all interconnected at what was called the Federal Internet Exchanges, 2 of them for redundancy. So by the end of the 1980s, we had extremely vigorous networking going on in the United States. So towards the end of that time frame, we were starting also to see academic networking in Europe and in Asia, in particular the wide network in Japan and the Norginet in the northern part of Europe that connected the academic networks of the 5 Scandinavian countries in Europe, including Iceland. So we have this very vigorous networking activity taking place in the network, and also towards the end of that time frame in 1988, we were able to get permission to connect a commercial system up to the NSFNet backbone. Up until that point, late 1988. It was only permitted that government-sponsored researchers, including military, could have access to this system. And I got permission to connect the MCI mail system, which was a commercial email service, to the NSFNet in order to figure out if we could get the email systems to interwork. And of course, that broke the appropriate use policy that said no commercial traffic is allowed on the government-sponsored backbones. That was important because in 1989, 3 commercial internet service providers popped up, UUNet, PSINet, and SurfNet, in order to sell internet service. And a few years later, in 1995, the NSFNet was terminated in favor of having the universities and their intermediate level networks simply get access to each other through public commercial systems. Similarly, the ARPANET was shut down in 1990 and replaced with alternatives. So this is a very important observation that the academic community and the research community really underwrote the cost of development and then facilitated the movement into commercial internet service. I think it's also important to recognize that in 1991, Tim Berners-Lee released his first instance of the World Wide Web. And 2 people at the National Center for Supercomputer Applications, Mark Andreessen and Eric Bina, saw the browser that Tim had developed at CERN and said, what if we made it a graphical browser with a graphical user interface, which of course is what you're all seeing today. So they built something called Mosaic, and it was wildly popular because it made the internet look like a magazine with formatted text and imagery and eventually streaming audio and video. So Jim Clark, who was the founder of Silicon Graphics, took one look at the Mosaic browser and said, this is a big deal, brought Mark Andreessen and others over to the West Coast to start Netscape Communications in 1994. The company went public in 1995. The stock went through the roof and the dot boom was on. Everybody in the Silicon Valley was throwing money at anything that looked like it had something to do with the internet. And this rapid escalation of investment continued until April of 2000, when a lot of the companies that got started to take advantage of the internet went out of business because they ran out of capital and they didn't have any revenue generator running at the time. So there were a lot of dead bodies lying around, but there were a number of companies that survived. Google is one of them, started in 1998, and before that, Yahoo. So there were survivors of the dot boom and the dot bust. Whoops, I'm trying to get to the next slide, and there we go. So this is what the internet kind of looks like now. Actually, this picture was taken a while ago, almost 20 years ago. It's a rendering of the backbone routing tables to show you the connectivity among the 100,000 or so networks that make up the internet. The point I want to make with this slide is that these networks are all operated completely independently of each other. They each have their own business models. Some are, for-profit, some are run by governments, and some are nonprofits. They all choose what hardware they want to use, what software they want to use. They decide who they're going to connect with on whatever terms and conditions they're willing to agree to. This is entirely distributed. It's not centrally controlled at all. The only reason it works, of course, is they're all using the same internet protocols. There is only one source of central management in the system, and that is to make sure that domain names get assigned uniquely to only one party. And similarly, the internet protocol numerical addresses get assigned uniquely to one party and not two of them, so you avoid ambiguity. But that's process is undertaken by the Internet Corporation for Assigned Names and Numbers. That's the only point of centralization in the system. Some people ask, how does this work? And I've been looking for a simple metaphor to explain this concept, and it's actually not too difficult. If you think about postcards, virtually everything you know about a postcard is applicable to an internet protocol packet. Postcard has a to and from address and some content, so there's an internet packet. If you put a postcard in the post box, there's no guarantee it comes out the other end. It's a best effort service. This is true of internet packets. They sometimes get lost. If you put two postcards into the post box and addressed at the same destination, they don't necessarily come out in the same order you put them in. This is also true of internet packets. They can get out of order as a consequence of alternate routing, for example. There is something else the internet does that the post office doesn't do. Sometimes you put one packet in and you get two out, partly because of retransmissions to overcome apparent loss of a packet. So you could reasonably say, why would anybody want a service like this? It gets things out of order, it loses things, and it duplicates things. But in fact, the way you make it useful is that you put another layer of protocol on top called the transmission control protocol. And that disciplines this otherwise unruly underlying postcard layer. And the way TCP works is easily illustrated. Suppose you have a book and you want to send it to your friend through a postal service that only has postcards. So you'd end up cutting up the pages, gluing them onto the postcards, and then you'd notice that not every page has a page number because you cut them up. And you know that the postcards could get out of order, so you number every single postcard 1, 2, 3, 4, 5. Then you keep copies because you know some of them might get lost. And then you start sending postcards to your friend. And then you figure, how do I know if I need to send any duplicates? And you get this brilliant idea. Well, you'll have your friend send a postcard back saying, I got everything up to postcard number 420. And then you realize that postcard might get lost. And so you say, well, what do I do then? And you say, well, I'll look at my watch and time out. If I haven't heard anything from my friend, I'll start sending duplicates until I get a confirmation back that my friend has gotten the packets or the postcards that I've sent. Now you know how the internet works. Oh, I did leave out one other thing. Suppose, for the sake of argument, that your 1,000-page book turned into a 2,000 postcard stack, and you took it to the post office, and by a miracle, the post office delivered all 2,000 postcards to your friend on the same day, except that you don't fit in his post box, and some of them fall on the ground and get blown away, or they get chewed up by the dog. And so you have an agreement with your friend that you won't send more than 200 postcards at a time until you do get an acknowledgement back. That's called flow control. Now you know how the internet works. I've left out some little details like how the heck does routing work, and what about the domain name system, and how do I do lookups and translate domain names into internet addresses. But you get the point. It's a layered architecture. And the thing I want to emphasize for you is this third bullet about the stupid network. We made a deliberate decision that the internet protocol layer, the little electronic postcards, have no clue how they're being carried. There is no indication in the internet protocol that this packet is going over an optical fiber, a satellite link, a radio channel, or a free space laser. And that was very deliberate because at the time we were doing this work in 1973, we knew there would be new telecommunications technologies coming. We just didn't know what they were. And we didn't want the internet to be bound to any of its historical bearing transmission systems. And so we said the internet protocol layer does not know how things are being carried. That might mean that you don't get the maximum efficiency out of the system, but it does give you massive flexibility to sweep new technology into the system. The second decision that we made is that the packets have no idea what they're carrying. Well, they know they're carrying a bag of bits, but they don't know what the bits mean. So the meaning of the underlying traffic flows is the interpretation of the content of those packets is done at the edges of the net, at the host computers, and not in the net. So if somebody invents a new application, the network doesn't have to change because it doesn't know anything about applications. And those two decisions about the lack of knowledge at the internet protocol layer has been vital to the ability of the internet to adapt to an incredibly broad range of new applications, some of which we're using right this moment, and which are only possible because the internet was capable of scaling up in terms of bandwidth and total number of hosts and total number of users. We also kept a completely open protocol stack, which meant you could extend the protocol layers horizontally by adding new protocols at a given layer, or you could add new layers of protocol, which is what Tim Berners-Lee did when he added the hypertext transport protocol above TCP/IP to introduce the World Wide Web. So this flexibility and openness is vital to the internet's success. Now, of course, we're faced with this massive influx of devices that have internet capability. And sometimes it's called the Internet of Things, sometimes cyber physical systems, which Ram knows a lot about because some of what he does at NIST is very much involved in cyber physical technology, plus, of course, artificial intelligence and machine learning. And I would draw your attention to the next bullet here and suggest to you that one of the obligations that we as technologists have, if we're building systems like this, is to make sure they're reliable, safe, they protect people's privacy and security, they're interoperable across brands of equipment, and finally, they have autonomy in the following sense. Imagine that you have a house full of IoT devices and you're relying on them to work. And one day the internet connection to the house goes away because somebody cut a backhoe through an optical fiber. Your house should not stop working just because the internet access has gone away. That's what I mean by autonomy. It's important for these devices to be capable of running without internet access. You might have an impaired operation, maybe you can't reconfigure things, but at least it still works. The second bullet is what we're living with today and have been for some time now, and that's the rapid propagation of misinformation and disinformation in the social media especially. Like Facebook and Twitter and YouTube and so on. This is an area of great concern and contention on an international scale, to say nothing of national debate. We're seeing that debate unfolding literally yesterday in the Congress during the hearings at the Congress. So the question is what to do about this, and it's not an easy problem to solve. Some people will wave their hands and say, won't artificial intelligence solve the problem? And the answer is no. No matter how carefully you do machine learning training and things like that, it's not always possible to correctly discern that something is false information. And I would appeal to all of you who are in the scientific disciplines, which is probably most of you, that we suffer from the following scenario. Let's imagine I go to Ram 10 years ago and I tell Ram I've got a problem, and Ram says, what's your problem? I tell him my problem and I ask him, what should I do? And he says, based on his experience, that he thinks I should do X for some value of X. And so I thank him for that and I go off and I try his remedy. And then 10 years later, I come back and I say, Ram, I tried X and it sort of worked, but I still have a problem. And at this point, Ram might say, well, I've had 10 years to further research this problem, and now I think you should do Y, which is different from X. Now, there are two possible reactions here. One of them is that the party says, oh, thank you. I'm happy to have the benefit of your 10 years worth of additional research. I'll go off and try to do Y. A different reaction, unfortunately, is not too uncommon, and that is, so you lied to me when you told me about X, and now I won't believe you about Y either. The problem is that science is not absolute. Science is the best approximation we have to the way the universe works right now, and we keep changing our models and our theories based on the feedback we get from experiments that sometimes falsify our theories. And as good scientists, we have to reject theories that we've been hanging on to for the last decade or three when we are confronted with evidence that shows that those theories are not adequate to explain the real world. Which leads me to the notion of critical thinking, which is one way of dealing with misinformation and disinformation, is to teach people, kids in particular, to think about the information that they are discovering or confronted with, and ask questions like, where did this information come from? Is there any corroborating evidence from legitimate sources? What motivations might someone have had to put this information in front of me? Are they trying to convince me of something that is not in my best interest or is somehow inimical to reality? These are practices of critical thinking, which I suggest to you are similar to practices of good science. And so this is something I wish that we could get our world population to be trained to think in those terms and to think first about these important questions about the information that we are exposed to. And that is a portion of a more general notion of digital literacy. The literacy that I'm talking about applies broadly across all media, but it's especially important in the online world because of the dynamics of the online world is somewhat different from what you see with passive media, where you're listening to radio, watching television, or reading a book. So for example, in the social media, there is an information reward structure, feedback loop, where, for example, in the case of Twitter, how many followers you have is an important metric. In the case of YouTube, how many views of your video did you get? And in the case of Facebook, how many likes are you getting? How many followers do you have? The problem is that in order to get attention, people tend to do things that are extreme because extreme things get attention. I think you may remember, paraphrasing Mark Twain, who said that lies propagate 3 times around the world while the truth is getting its shoes on. And in a sense, I think he's right about that, because bad news, which is usually warnings, we have learned by evolutionary means that to take warnings seriously, because if you don't take them seriously, it could be fatal. So knowing that that's a bear and you should run the other way should not require a great deal of mental activity to analyze what species the bear is and how many family members there are in the neighborhood. Mostly it's run like hell. And so we have learned evolutionarily to take on warning information seriously and quickly. And the same is true now for, unfortunately, disinformation and misinformation, which comes in the form of warnings. And that is what drives a lot of the misinformation and disinformation today. Now, there's more work to be done in this environment. What's happened is that the internet has been so successful that it has uncovered a variety of challenges that these online environments pose that have analogs in the real world, but often not necessarily at the scale that the internet poses. So we have real problems, for example, with harmful behaviors that cross international boundaries. We have a victim in one country and a perpetrator in another, and now we need collaboration across international boundaries to track down perpetrators. We need agreement that the perpetrator is in fact at fault and should be apprehended. So that's going to require a lot of negotiation to come up with common agreements about dealing with harmful behaviors in the online environment. The malware, of course, and buggy software are the reason that we have so many problems, because the bugs in the software are what the bad guys exploit in order to hack into our operating systems and get our credentials and steal our money, or mislead us in some way or another, or inject bad information into scientific processes and spread disinformation about vaccines against the virus. So malwares and buggy software are a real problem. And I'm sorry to tell you that those of us in the programming discipline have failed miserably over 80 years to figure out how to write software that has no bugs. So this is an area of real concern. We need much deeper research into programming environments that will expose mistakes that could be exploited later before they actually get out into the field. And you can see how severe this could get, especially now as you see machine learning and artificial intelligence applied to things like self-driving cars and self-flying drones and robots. Errors in the way they behave could have fatal consequences. So again, there's a huge ethical obligation that I think software programmers and companies that sell software-based products should feel a burden, an ethical burden for assuring that that software is as bug-free as possible, and furthermore, if the software does get out into the field and bugs have been found, there needs to be a way to update the software to get rid of the bugs. And that, of course, leads to another problem. How does the receiving device know that the update is coming from a legitimate source and not a bad guy? And second, how do they know whether the data actually arrived intact as opposed to being modified on the way? Digital signatures will help us there, both to authenticate sources and to verify the integrity of the software. So there's lots and lots of work to be done. This is simply a manifestation of some of that work that we need to do. There's also a big problem that we just don't have internet access uniformly across the planet. And there are a bunch of reasons why it's not uniformly available. In some cases, its physical infrastructure just isn't there. In the rural parts of the United States and other parts of the world, you often find no access at all because of the cost. That's another economic barrier. You could put in optical fiber, but it would cost so much that nobody could afford it. Again, how do we drive cost out? How do we develop new technologies that are less expensive and more affordable? Sometimes policy inhibits the propagation of internet access. Sometimes the government doesn't have a regime that allows for competitive investment by multiple parties. Sometimes the government isn't willing to invest and defray some of the cost of building infrastructure. And so we don't get the build out that would be necessary in order to provide access for everyone. And finally, even if you have access, the question is, do you know how to use it? Can you use it advantageously? Could you use it to earn a living? And that's a function of whether or not you have the educational background in order to make best use of these capabilities. And so these are among the various reasons that we still have a digital divide, both domestically and in the rest of the world. Now, here's something that I was quite surprised to discover, and that's the rapid investments being made in undersea cable. I've been watching this, optical fiber development for the last 40 years, since the early 1980s, and I was astonished to see the amount of undersea capacity which is going into and under the water in the oceans. And I will say that the costs have been driven out is sufficiently that companies like Google and others, Amazon and so on, can actually build their own optical fiber cables without having to share it or find a collaborator to pay for it. And I don't have a slide here, but if I did, the next slide would show you satellites in orbit, notably Starlink, which has announced a plan for 42,000 satellites in orbit, and there are several others. Cooper is one, OneWeb is another. So low Earth orbiting satellites, in addition to the MEO and GEO satellites, are already up there. Sounds like we have a little more interference again. In any case, we're seeing the massive plans for low Earth orbiting satellites. And what that means is that it may be impossible to escape access to the internet, even if you're at the North or South Pole. So frankly, I'm looking forward to that situation. This is a lesson from being in Washington for the last 45 years. I moved here in 1976, and I can tell you that this aphorism has a certain amount of weight. I mentioned the IoT before. These are just some examples of devices that have internet capability, but the one I was most amused by is the guy that built an internet-enabled surfboard. Apparently, he was out on the West Coast and he's got bored sitting on the water waiting for the next wave. So he put a laptop in the surfboard, put a Wi-Fi service at the rescue shack, and now he sells this as a product. So you can surf the internet while you're waiting for the next wave. And I used to tell jokes that every light bulb would have its IP address someday. Ha ha. Well, guess what? Now we have light bulbs with internet addresses in them, and they're remotely controllable, and of course, lots of other devices. Now, I made a list some time ago of various things that I thought you could do with internet-enabled capability, appliances. But the one I thought was the most interesting is the internet-enabled sock. Imagine that you have an RFID chip in the sock and you could send a pulse around the house and find out that the missing left sock is under the sofa in the living room. And so I figured this is a huge contribution to humanity, that you can find the missing sock. And so I will go down in history as the guy that enabled people to find their missing clothing. I want to spend a little bit more of time and then allow for some Q&A if you have any. This is not a speculative story. This is a story that starts in 1998, the year after the successful landing of the Pathfinder robot on Mars. Now, some of you, I'm sure, will remember that the previous successful landings were in 1976 of the two Vikings that reached the surface of Mars and transmitted data back. And then nothing worked for some 20 years. And finally, the Pathfinder landed successfully in a big bouncing balloon. I remember thinking when I saw that if I'd been the program manager sitting in my office when somebody came in and said, "Hi, we're going to deliver your $6 million robot in a bouncing balloon," I would have thrown them out of my office, but it worked. So I got together with a team at the Jet Propulsion Lab in the spring of 1998 after the Pathfinder had landed the year before. And we asked ourselves, what should we be doing now, that is to say in 1998, in order to be ready for what we will need 25 years later, that is to say in 2023. So we began thinking about how to build an interplanetary internet. How could we build a network that could span the solar system and support manned and robotic space exploration? We started out thinking we could use TCP/IP because it worked on Earth, so surely it would work on Mars, and it probably would. And then we started doing the math. If you look at just Earth and Mars, when we're closest together, of course, we're 35 million miles apart. It still takes 33.5 minutes for a radio signal to propagate back, and then, of course, another 3.5 to come back at the speed of light. And when we're farthest apart, it's about 235 million miles, which is about 20 minutes one way and 40 minutes round trip. There's another little problem. The planets are rotating, and we don't know how to stop that. And so if you're trying to talk to something on the surface of the planet rotates, you have to wait till it comes back around again to talk to it. So we have a variably delayed and disrupted environment in which to build networking protocols. And TCP/IP was too brittle for that, among other things. The domain name system also was not well suited to this potentially high latency and certainly variable latency and disrupted environment. So we ended up developing a new suite of protocols that we call the delay and disruption tolerant networking, in particular the bundle protocol and the Licklider transport protocol, which is a layered structure kind of like TCP/IP. Those protocols were in prototype form around 2004 when the other Spirit and Opportunity rovers landed on Mars. You'll remember in January. The radios were intended to transmit data from the surface of Mars back to the Deep Space Network, the big 70-meter dishes at Goldstone, California, Canberra, Australia, and Madrid, Spain. The radios on board the rovers began to overheat, so the engineers had to back off on the duty cycle. It had only been rated at 28 kilobits a second to begin with, and so the scientists were now more grumpy than ever. And then somebody pointed out that there was an X-band radio on the rover, and the orbiters, which had been sent before in order to map the surface of Mars, still had functionality. X-band radios had memory and processing and communication. And so the JPL team reprogrammed both the rovers and the orbiters to become a store and forward network. So the rovers would hang on to data, so the orbiter got overhead, then transmit the data to the orbiter. The orbiter would hang on to the data until it got to the right place in its orbit to transmit data to the Deep Space Network. And so this was a packet switch store and forward network using prototype software intended ultimately for the interplanetary network. In the meantime, from that period, from 2004 to the present, we have been refining and standardizing the interplanetary protocols. They've been fully standardized by the Consultative Committee on Space Data Systems, which includes JAXA and ESA and NASA and the CARI and Korea and the other spacefaring nations. And also we've standardized them in the Internet Engineering Task Force for terrestrial use. Those protocols are now freely available on GitHub or SourceForge. All the documentation is freely available. And we have been using the prototype store and forward software on Mars for subsequent missions like the Mars Science Laboratory, Perseverance, which just landed. It's anticipated that the new bundle protocols will be available for the Artemis mission, which we hope will launch sometime in the mid to late 2020s to return to the moon. And then subsequently, of course, we hope to see these same protocols serving an arrival at Mars probably in the 2030s. So our purpose here is not to design, build, and deploy an interplanetary backbone, but rather to put those protocols into spacecraft that have been launched for specific missions, scientific missions, but when they complete their missions, they can be repurposed, just as we repurpose the orbiters in Mars, to become nodes in an interplanetary backbone. And in the recent discussions, we've even discussed the possibility of using small sats and deploying them deliberately in configurations that would be advantageous for supporting future missions in the subsequent decades of the 21st century. So that's the up-to-the-date discussion about the interplanetary system. And I'm happy to stop here and switch over to Ram or whoever wants to manage the Q&A part of this discussion, because we now have about, well, 20 minutes, I think, if we want to use that much of it.
Thank you again, Vint, for the insightful talk. And maybe we can stop sharing now. And let's.
Yeah, I have to find the right place. Yeah, there we go. Okay.
Great. Thank you very much, Vint, for that really insightful talk. And also, I think you showed a lot of stuff on the interplanetary travel. And I believe that you participated in Gene Roddenberry's Earth, the Final Conflict. And you probably appeared in one of the Star Trek shows. I don't know, hopefully.
You know, what's interesting is that the episode that Major Roddenberry asked me to appear in was called Disaster. So I don't know whether that was an implicit message or not. Let's see. I see a whole bunch of comments in the chat. How do you want to manage this?
So what I'll do is, Vint, I'll probably select a few of them to ask you, because we have about 20 minutes. And then towards the end, Meena, who's the president of Washington Academy of Sciences, will close the meeting. So let me see. One of the things you mentioned is about the software, as the malware involved in all this software and the software bugs. So, and that's going to, and you, in your opinion, that is going to be a big problem in the future. In terms of, if you don't resolve the problem of software bugs, then we are in trouble. That's what you're saying.
Well, I think we will not ever solve the problem of absolute certainty that there are no bugs in software. For one reason is that when software gets placed in an environment for which it was not intended, it may expose bugs that we didn't anticipate simply because we didn't anticipate that particular use case. However, I think we can improve our software development environments to help expose some of those mistakes. Some of them are really stupid. I mean, I don't know about you, but I have a little dent in my forehead from the many times when I've discovered a bug, you know, thinking, how could I be so stupid? Oh, I'm so sorry about this. I thought I'd unplugged the phone. Hang on one. Okay, sorry about that.
And yeah, associated with that, actually, Ravi Sharma has a question in terms of cybersecurity. One of the things that happened when internet was designed is cybersecurity was not taken into account when your initial design. So, but then that's becoming more and more important, as you have pointed out, with a number of problems which are occurring. And so what is being done in that area?
Well, first of all, it's incorrect to say that security wasn't taken into account. For one thing, we were doing this work for the Defense Department, and we knew the intent was to use the system in command and control. So you can be sure we were concerned about security. However, two things. First of all, we did a classified design which made use of classified crypto equipment from the National Security Agency and techniques which we weren't allowed to share publicly. But we were looking and did do experimental work in a secured system, including link crypto and end-to-end crypto and packet crypto and all that other stuff. But then the second thing that's important to understand is that it was in 1976 that the first paper was published on public key crypto by Marty Hellman and Whit Diffie. Of course, some of you will know that the idea of public key crypto was actually invented before that, around 74 by GCHQ, but they didn't advertise it. So Marty Hellman and Whit Diffie get a lot of the public credit. The point I want to make is that while I was running this program at ARPA, public key crypto was not available yet. And I needed to get the protocols as they currently were instantiated in place so we could demonstrate, for example, that 1977 capability to be persuasive about the basic technology. So it's not like we didn't care about it or didn't pay attention to it. It's just that the timing wasn't very good. On top of which, imagine that this thing was being developed during that period by graduate students for the most part. And I challenge you to get graduate students to be disciplined enough to handle crypto keys in the way that is necessary. And if I've insulted any graduate students in this call, it was deliberate. So, and besides, I was one back then. So now, final point is that we have retrofitted, we knew we could do this, we have retrofitted a significant amount of cryptographic capability into the system. There's IPsec, there's DNSSec, there's TLS, there's QUIC. There is the BGP and the RPKI routing background stuff. There's a whole lot of stuff going on to introduce security into the system. But it takes discipline, and we have to give people tools to make it easier. For example, two-factor authentication adds a certain amount of annoyance to doing logins, because it's not just username and password, but in its absence, you're at risk. And if you're willing to do two-factor authentication, you're more protected. So I will challenge that we did not pay attention to security, and we continue to pay attention to it today.
Thank you, Vint. Actually, I stand corrected. Ravi kind of indicated that cybersecurity of being paramount. What measures can we develop to protect critical infrastructure and services? That's actually what his question was, and it was my mistake. I misinterpreted his question. So anyway, you answered that. So let's go to the next one. Emmanuel kind of wants to know, what do you think of IPv6?
Well, it's been a slow process. Those of you who watched the sausage being made might remember that it started in 1992 when we all agreed that we were going to run out of the IPv4 address space someday. And, you know, it's funny, when Bob and I did the original design, we actually tried to calculate, you know, how many terminations should we plan for. And in 73, we estimated that we said, well, there'll be 2 networks per country because we thought there should be competition. And we didn't know how many countries there were, and we didn't have any Google to ask. So we guessed at 128, which was wrong. And then two networks per country is, 256. So that's 8 bits of network address. And then we said, how many hosts? And remember, it's 73. Computers are big, giant air-conditioned room things. So we said, well, how about 16 million, just to have a big number. And so that's a 32-bit address space, 4.3 billion terminations, which is more than there were people on the planet at the time. Now, of course, we know we need much more address space. And so IPv6 was agreed in 1996. I thought everybody would instantly recognize the utility of switching to that. And of course, they didn't. And the reason they didn't is they were in the middle of the dot boom, and they were much more interested in building applications and getting capital from risky venture capitalists than they were in re-engineering for IPv6. So now we are about 30% penetrated. It varies dramatically from net to net. I'm going to argue, though, that at some point the mobile telephony and the IoT will drive us to IPv6, because we simply can't keep using network address translation for the tiny little 32-bit address space that exists. And just to give you a concrete example, at Google, we actually had to switch from v4 to v6 in the core of our network because we ran out of address space in our own internal network and couldn't support it with IPv4. So I think we'll get there. It's just been a long slog.
Yep, thank you. And then Saujanya has another question, says, you invented the internet, and that's considered a revolution. What revolution you see coming next?
So can you spell computational X and then put X in and put something in to replace X? I think that revolution is well underway. Computational methods for the application of computing is a rapidly evolving field, and that is a huge revolution that is already underway. I think if you also add to that the revolution in biotechnology, our understanding of genetics, not only the genome, but also all of the proteome, and now the biome, and of course the brain technology and the connectome. All of those things are well underway. They will be the underpinnings of massive revolution over the course of the next several decades. Even something as let me say, simple as electroneural interfaces is becoming very important. My wife has 2 cochlear implants, and they work spectacularly well, and they only work because we understand how our auditory nerve is stimulated to produce pulses that the brain interprets as sound, and we can fake that process by building computers that generate the same pulses and the brain correctly interprets as sound. Same arguments could be made for ocular implants and for eventually spinal implants to recover motor capability. So those are the kinds of revolutionary things that I am convinced will happen. Some people will say, well, you should add artificial intelligence and general artificial intelligence. And while I will agree that machine learning has done some very impressive things, well beyond simply playing games, I think that they are still brittle and uncertain and often behave in ways that we can't predict. And so that revolution, while it's underway, it still has a long way to go before I think we can reliably assume that those systems can be depended on.
Yeah, in fact, continuing that, Brian asked a question that people are inherently lazy. I do not have much confidence on people to apply critical thinking because they consider it as work. So should we create an AI control misinformation and disinformation system? Because you mentioned about misinformation happening on the internet.
This presumes, of course, that artificial intelligence is capable of doing something that humans being are either unwilling or incapable of doing. And I will tell you that my experience in general is that AI could stand just as well for artificial idiot. This is not to diminish the amazing accomplishments that many people have demonstrated with machine learning, in particular deep neural networks. But as again, I will say that they are based on training mechanisms, which are mostly about establishing correlation. And so machine translation, for example, is all about correlating a phrase in one language with a phrase in another language. It is not necessarily about understanding. We are creeping up on the understanding element. Certainly Google Assistant, for instance, which is an oral interface to the Google knowledge base, is increasingly capable, but it still makes some funny mistakes. We use a knowledge graph of a couple of billion nodes in order to capture knowledge, capture factual information and apply it. We use that, for example, to enhance the queries that people make to our search web search database so that we actually expand the search to broaden it to a wider range of terms in order to get a better answer back for people who are asking questions. I still think we should be cautious about AI. And so I'd much rather get people trained to value critical thinking. We need a society where critical thinking is in fact admired as opposed to treated as too hard to do.
Yeah, in fact, that was the next question from Sudarshan. You answered it already. There's another question by Sancha who says that will the Starlink project by SpaceX eliminate the need for underwater optical fiber network?
Absolutely not. Even though it's a wonderful piece of work, and the data rates are appreciable, they're in the hundreds of megabits a second, but the undersea fiber is carrying hundreds of gigabits per second, 400 gigabits per second, and it's soon to be a terabit per second. We're not going to see anything like that on the Starlink system. On the other hand, Starlink is going to give access in places where we'd never be able to pull fiber or even put in point-to-point laser links. And so the two are very complementary. Moreover, they are backup for each other. And I think we will still have anchors snapping cables as has happened in the past, or deliberate cuts. And so the satellite capability is a really valuable adjunct to the undersea fiber.
Yeah. So there were, again, we have maybe time for a couple of quick questions. The number of questions about the quantum information and the internet. Do you have any comments on that?
So I think the answer is unlikely, and let me explain why. First of all, everyone should understand that entanglement is not the equivalent of transmission of data. It's a correlation. And in order to make use of it, you have to deliver, for example, an entangled photon to a target before you can use the correlation between the Earth-based photon and say the Mars-based photon. And even then, you're not communicating any information. It is possible to transmit information using entangled photons. That's what the quantum internet is about. Right now, the big problem there is that the distances over which you can transmit a photon that has retained its entangled state is limited. And if you want to convey that information beyond the point where the entanglement would dissipate, you need quantum repeaters. And those are still experimental and not yet functional. So I don't really anticipate quantum communication as being an important tool for deep space communication. I think mostly it's going to be conventional stuff. We are all eager, however, to move to optical from radio, because optical comms has much higher bandwidth. The problem there is pointing accuracy and proper timing, because we have to lead the planet, for example, and whatever the telescope is that's going to receive the optical signal. We have to know where to aim it, so that when the signal actually gets there, there's something to receive it. So pointing accuracy is very important, but we're all very, very eager to get to optical for higher speed.
Yeah, thank you. That also answers the question which Ankur asked about moving towards optical. And finally, this is kind of a little bit of provocative question from Terry. He wants to know if how unhappy Google will be if the network infrastructure were to be nationalized. But you may not want to answer this question, but we just posted it on the. So Terry's question was, would you be unhappy if Google were to be nationalized? I guess there's a network infrastructure associated with Google, so that was the question. But
well,
it's a kind of a provocative question, in terms of a controversial question.
Well, let me make sure I have understood the question. Are you asking about the infrastructure associated with Google or something else?
Probably.
You said, you said that there was that Google had discovered it had to buy some of its own bandwidth, that it actually was using, it had an internal network, and you were delivering services through that to the rest of the internet. So I just wondered if, and I was using yours as an example, but I've always thought that the internet should be a public utility. And would you be unhappy if Google became a public utility?
Well, Terry, let's distinguish between the use of the protocols for a moment and the public internet. And there's nothing that says you can't build a TCP/IP based network, a private one, for your own purposes, which is what we have done. We've built a private network that links all of the data centers together. We built another network which links the data centers to the public internet. And we use that same mechanism to connect to the other carriers, and we also use that in order to do content distribution, which is what you see Akamai doing as well, and others who put servers in the various internet service provider locations in order to provide commonly accessed data with lower latency. So I think it's a misunderstanding if you think that somehow it's wrong to have a private piece of TCP/IP infrastructure in place in order to build the network to connect the data centers to each other. We move data back and forth constantly in order to replicate the data and make sure it doesn't get lost. And even if a data center is lost, you don't lose any data. But then we also interface to the public network. as well. And I don't understand an argument that says you can't have a private network that uses these same protocols in order to build your infrastructure and your applications.
I'm just talking about a public internet service that doesn't require me to sign up with AOL or whoever.
Terry,
Well,
I think,
you don't have to. I mean, you don't have to sign up with Google. You don't have an account to use it.
Sorry,
yeah,
I'll back out now.
Yeah. So anyway, thank you very much, Vint, for that response. And I think we need to close off now, and I'm handing it over to Meena for her closing remarks. Meena is the president of the Washington Academy of Sciences.
Thank you, Dr. Cerf. I just want to thank you for your insightful and intriguing talk. We really appreciate and grateful to the time that you spent with us this afternoon and educated us about internet. Without hesitation, I would say your contribution to science and the field of internet has impacted our lives, our everyday lives, not only for this generation, but for generations to come. We're truly honored to have you as a member of Washington Academy of Sciences, and simply thank you again.
Well, thanks so much for inviting me, and I will pay my dues today, so I won't lose my membership.
And thank you very much again, Vint, for that little advertisement for the Washington Academy of Sciences. And we are glad to have you as a fellow of the Academy too. Thank you again.
Take care, everybody. Have a great rest of the day.